Okay, so what we're going to go through right now is example 15.4 in your book. And what we have is we have two cars, car A and car B, and they're traveling towards each other at those given velocities. And what I'm showing here are the momentum diagrams before impact and after impact. So before impact, we have car A with a mass of 15,000 kilograms traveling to the right at a speed of 1.5. So the momentum diagram for particle A is mass times velocity, which is the 15,000 kilograms multiplied by 1.5. Particle B is the purple block, and that one is traveling to the left at 0.75 meters per second. So we have a mass of 12,000 kilograms multiplied by 0.75 gives you the momentum along the x direction, but that's going towards the left. Now after impact, they couple together so they do not separate. So both of these boxes then are stuck together. So you see the purple and the green are now together. So after impact, what we have is we can combine their masses. So we have 12,000 plus 15,000, and we multiply that by a common velocity that's through the center of mass of V2. And we're going to assume, for just the sake of setting up the problem, that the combined velocity will be going in the positive x direction after impact. What we need to solve for in this problem is we want to figure out what this common velocity is, this V2, after impact. And we also want to figure out what is the impulsive force between them if the coupling takes place in 0.8 seconds. So what we're going to use is we're going to use the conservation of linear momentum to solve for V2. And then we'll use the principle of linear impulse and momentum to figure out what the average force is between them when the coupling takes place in 0.8 seconds. So using the conservation of momentum, you can see that we have ma va plus mb times vb, so that's the initial momentum for both particles. That equals now the combined momentum. So we have the combined mass times a common velocity v2. So I'm just going to plug in the values that we had on our momentum diagrams. 15,000 times 1.5 is the momentum of particle A. 12,000 times now a minus 0.75 because the minus we're showing is going in the opposite direction, so in the negative x direction. That equals the combined mass of 15,000 plus 12,000 times our final velocity v2. So solving this, you see that the velocity, the final velocity of both cars that are coupled together is 0.5 meters per second, and it comes out to be a positive answer. So we were correct in our diagram where we stated that it was going, the final velocity would be to the right, to the positive x. Now, the second part of our question asked what the impulsive force was. So that coupling force, what is the coupling force between the two cars? So in this case, what we have to do is we're going to have to draw a diagram of one of the cars. So we can isolate either car A or car B, and we can draw an impulse diagram showing the impulsive force and the time, and then we can use linear impulse and momentum to solve for that impulsive force. So here I'm showing the impulse diagram for car A. So I'm isolating car A, and what that does is it exposes this impulsive force from car B onto car A. And you see that this impulsive force is what we need to solve for, and the time is 0.8 seconds. So I'm showing it going in this left direction because that is the direction of force from B onto A. I'm also showing the weight. The weight going down is also a force in the y direction. In this case, we are not going to use that force. We're only going to use the x direction of our force. So if we plug in our values, we can see that the initial momentum of A is just our mass times our velocity in the x direction, plus we have our sum of the forces in the x direction, which we only have a negative F, that's our impulsive force, times our time, which was 0.8 seconds, and that's going to equal our final momentum for car A, which is the mass of 15,000 times the final velocity, which is 0.5. Then when we solve for F, we see that the impulsive force between the two cars is 18.8 kilonewtons. So that completes this example. Now in this second part, we isolated car A, but you could just as easily draw a impulse diagram of car B, and then you would show a positive impulsive force from car A onto car B, but it would come out to be the exact same answer. So I encourage you to try that. Try setting up car B and isolate that, and do your impulse and momentum equation for car B, and you should solve for the same answer of 18.8 kilonewtons.